Question 1. When two or more waves are at the same place at the same time, the resulting effect is called A. A standing wave, B. A Doppler wave, C. A shock wave, D. An interference, E. A period. Correct answer is D. Interference. So, when you look at this conceptually, you have one wave going to the right, and you have another wave going to the left, and they could be the same frequency, they could be different frequency, they could have different amplitudes, but either way, when they meet at this point right here, they will interfere with each other's paths, either causing a frequency change or an amplitude change. Question 6. A certain ocean wave has a frequency of 0.07 hertz and a wavelength of 10 meters. What is the wave's speed? So in order to find the velocity, you use the equation V equals F times the wavelength. In our case, velocity would equal 0.07 times 10. 10 is the wavelength, 0.07 is the frequency. When you do out that math, it gives you 0.70, which gives you an answer of V. Question number 7. Suppose a bug is jiggling up and down and swimming towards you at the same time. Compared to the frequency at which the bug is emitting wave, the frequency at which the wave is reaching you is B higher. This is because although the bug is emitting the waves, he's also moving forward, so he's experiencing each wave as it comes, and the waves are hitting you at a faster rate than they are hitting the bug. 10. The kinetic energy of the bob on a simple pendulum swinging in simple harmonic motion has its maximum value when the displacement from equilibrium is at what point in its swing. So when you look at a pendulum, here is 0, and then out here is both of its amplitudes, both of its highest amplitudes. Now, kinetic energy is energy of motion, and potential energy is energy that is stored and can be used. So when you're looking for the maximum value of the kinetic energy, you're going to be looking at 0 as the maximum, because these are the two highest potential energy, which means as it's swinging, here is where it has its highest magnitude. 12. Sound is an example of A. Longitudinal wave, B. Constructive wave, C. Doppler wave, D. Transverse wave, E. Standing wave. The answer is longitudinal wave. It is this because sound always travels from left to right, or it broadcasts itself out. So say you have a beacon that's creating sound. Any way that it goes, it'll create a sound that's circular. Or say it's got microphone or speakers on all sides, it would create a sound that's circular, which would broadcast out in a longitudinal manner. Or if it was a direct wave, it would still broadcast out in a longitudinal manner. Or if it was up, it would be a lateral, but still longitudinal. 13. As a gust of wind blows across a field of grain, a wave can be seen to move across the field as the tops of the plants sway back and forth. This wave is B, a longitudinal wave. So it goes back to the same concept as a sound wave being longitudinal. It's on a flat surface and the wind is blowing across it. And therefore the plants can't move up and down. The plants are moving side to side. They're swaying back and forth, which makes them a longitudinal wave. 14. If you double the frequency of a vibrating object, its period A halves. So when you look at the equation, velocity equals frequency times its period, you're going to take if the frequency is larger, then the period has to be smaller. If the period is larger, then the frequency would have to be smaller. So to equal it out, if you have double the frequency of a vibrating object, the period would have to half in order to keep the velocity equal, because the velocity will be the same. 19. Which of the following quantities is at its maximum when the object in simple harmonic motion is at its maximum displacement? And the answer would be B, acceleration. When it's at its maximum displacement, it's at one of its amplitudes. and that original position is 0. So when it's at one of its amplitudes, its acceleration is greatest, which is the same as on this side, its amplitude is equal to the greatest acceleration, and then in the center, it is equal to 0. A beam of light emerges from the water into the air at an angle. The beam is bent away from the normal. So this is the beam of light, and this is the water line. And what was explained was that it is in the water. It is a lot slower because it has a denser matter to go through, and when it enters the air, it will change a direction because it will quickly move into a different direction. For example, a lawnmower cutting some grass and in a driveway. This is the grass, this is the driveway. When you have the lawnmower and it's coming around and it catches one edge on the grass, it will quickly change directions, or it will change the direction of the lawnmower until both tires have reached on the grass, in which case it'll just go at a slower pace. The same thing applies to light exiting water. If you look at it as the light beam is coming into the water, it will change directions because it'll get slower, and one side of light wave will move away from the original beam, and then going out it'll move away.